Hey guys, let's talk about our factors affecting equilibrium. So this is a little less math. Awesome. At least in my opinion, it's awesome. Although I don't mind math at all. Let's talk about what happens when we change concentrations, when we change volumes, when we change temperature, when we have a catalyst. Okay. Now, I'm going to start at the bottom and work my way up. When I have a catalyst is present to make a reaction go faster. It's part of that kinetics part that we talked about a couple of minutes ago. There is no change. It affects both the forward and reverse reaction in the same way. And so there is no change to what happens at equilibrium. Okay? We can talk about changes in temperature. And we've talked about that. So when temperature changes, the value of the equilibrium constant changes. And so that may mean we need more product. It may mean we need more reactant. It entirely depends on what direction we're going to go. We also have some shifts that are going to happen because of the thermal stuff that goes with that, which we're going to talk about later. We'll talk about the thermochemistry for the third test. So there will be stuff that's related to that as well. So we'll be able to use that to make some predictions, but not right now. We can look at changes in volume and pressure. Now, this is really only important for the gases, right? Generally speaking, as we change the pressure, as the pressure goes up, it wants to alleviate that in some way. And one of the ways that it can do that is by having less moles of gas. So whichever side of the equation has less moles of gas, that's the direction we're going to shift. Changes in volume. If we make the volume bigger, there's more space for moles of gas. So that typically means that we're going to shift in the direction of more moles of gas for a bigger volume. For changes in concentration, it depends on what the change is. So if I up the concentration of my reactants, I'm going to have to go forward to get rid of that. If I decrease the amount of reactant, then I need to go backward to make up for it. Okay? Same can be true on the other side. So it depends on what change we're making and where that is, how that's going to affect what we're looking at for equilibrium. The easiest way to do that is the mathematical way with the Q that we talked about. But if we're just talking about, okay, I changed I upped the reactants, we should be able to predict which way that's going to shift so that we can deal with that. Okay. Now, this process is actually described as Le Chatelier's principle. His statement is that if a system at equilibrium is disturbed by a change in temperature, pressure, or the concentrations of one of the components, the system will shift its equilibrium position as to counteract that effect. All right. So we can zoom into this slide a little bit so that we can see this better. And what it says is that if our initial equilibrium is here, we have small amounts of reactants and a larger amount of product, but I add some more reactant to it, that additional reactant is going to drive me towards product. Now, the amount of product hasn't changed, but we're going to have to shift to make sure that we get to it. It's actually a principle that we used in the laboratory when we had that large excess for setting up the calibration curve for the iron thiocyanate compound. We force a large excess of the thiocyanate to drive that reaction to product. And that means that we know exactly what the concentration of the product is because it's based on the limiting reagent, which is the iron. So that shift is being driven by the fact that we have excess FCN or SCN. Okay. So that's how concentration can affect this. Now, if pressure goes up, right, if we squish it, the system shifts in the direction of fewer moles of gas. We just talked about that. Now, this next part is about the temperature. Okay. There are two ways that we can talk about a reaction. We can either talk about it as being endothermic or exothermic. Exothermic means it takes the energy that it has and it gives it to the surroundings. Endothermic means it takes that energy in. Okay, so if it's giving off heat, right, that means that heat is a product. So if I have a reaction that looks like this, and I say that this reaction is endothermic, that or exothermic, so it's giving it off. That means that heat is a product. Okay, so if I increase the temperature, that means I've added that means I've made the heat higher. That means it's going to shift this direction to compensate. If, on the other hand, it's an endothermic reaction, so I have heat plus AA plus BB goes to CC plus D, and I increase the temperature, that's going to drive that reaction forward. Okay, so it depends on what we're looking at in terms of endo and exothermic. We'll talk about that again more when we talk about the thermochemistry, but that is something that we need to be able to look at in terms of Le Chatelier's principle. All right, I'm going to zoom back out so that we can see more of our slides when we're going forward. We can apply Le Chatelier's principle in this type of fashion. So I am given a reaction, N2 plus 3H2 goes to 2NH3. Can you tell I like this reaction? It is an exothermic reaction. It gives off heat as a product. So if I add N2, what happens to that? Well, if I add N2, right, I have N2 plus 3H2 goes to 2NH3. And I'm not going to label the phases at this point because you can see them there. That's the only reason I'm not doing it. So if I add N2, so I increase the N2, then I'm going to shift forward. If I remove H2, so I bring that down, that means I'm going to have to shift backwards to compensate for that. If I put that into a smaller volume, that means that the pressure goes up. If the pressure goes up, I want to go to the side that has the least number of moles of gas. I have 4 moles of gas on my reactant side, 2 moles of gas on my product side. So it's going to shift to the side that has the fewer number of moles. All right. If I put it into a smaller volume, we just talked about that. If I increase the pressure, same thing, because we just talked about this. Remember that the volume and the pressure are inversely related. So smaller volume, higher pressure, smaller volume, larger volume, smaller pressure. Okay. So same thing if we increase the pressure. All right. If I increase the temperature, what happens? Well, remember, this is an exothermic reaction, so the heat is a product. So if I increase the temperature, that's going to shift that direction to compensate for that. And if I reduce the temperature, then it's going to go forward. Okay? So that's what we're looking for. It does not change the value of K, all right, in terms of Le Chatelier, but increasing the temperature will change K. So we're going to have to take that into account too, which is why we're going to talk about it more in the thermochemistry. But for now, we just want you to understand that if we add energy in one of these ways, that there is going to be an effect from Le Chatelier's principle. Okay? So that's that. Here's another set. I just want to ask some more questions. Oh, that's not what I wanted to do. I want to do, no, sorry. Doing the wrong thing. So now I have CH4, this is a gas, plus 2H2S, which is also a gas, gives me CS2 plus 4H2. And again, that's a gas, and that's a gas. If I decrease the concentration of H2S, so I decrease H2S, that means I need more H2S, so I'm going to shift in that direction to compensate. And you may notice that what I've done is I've set this up so that whatever I'm doing, I'm making the change. Like if I make it lower H2S, I put an arrow down from H2S, and then I draw an arrow to show which direction it's going to shift. That makes it easier for me to keep track of what it is I'm trying to do. If I increase the pressure, I go from 3 moles of gas on this side to 5 moles of gas on that side. If I increase the pressure, I want to go lower number of moles, so I'm going to go that way. If I increase the temperature, I don't know, because I don't know if this is an endothermic or exothermic, so I have no way of predicting. Okay. If I increase the concentration of CS2, then I'm going to go back to reactants, okay, because I've now made more product. And if I decrease the concentration of CH4, I'm going to get the same shift, okay? So remember, we can add things or take things away. There are ways that we can do all of those things. So we need to be able to predict what's going to happen when we make those changes, okay? Questions, comments, problems about that? All right, that takes us through our last topic before we start talking in detail about the lecture, or the lab. So the next thing we're going to talk about is the lab. Then I'm going to do some more problem solving on tape for you. I'm going to do those a little bit later. The problem solving, I'll come back to the problem solving. After we're done with this, I'm going to start on the next lecture, okay? But that should take you through everything for this except for the lab, which we will be back to in just a minute. Thank you for being with me, and I'll see you again soon.